There's something strange happening every time you sit in a chair. Not strange in an obvious way. Strange in the way that takes a physicist several years of training to fully appreciate, because the force you've been calling gravity your entire life, it may not be a force at all. And the moment you understand why, everything else about the physical world starts looking different. Here's what nobody told you in school: most of what we call mysteries in physics aren't mysteries at all. They're limits. Limits of measurement, limits of geometry, limits of what matter can do when space itself is involved. And somewhere in the middle of all that, we invented a word, gravity. And we acted like naming it was the same as understanding it. It wasn't. Let's start with something you felt. You've dropped something, a glass, a phone, whatever, and for just a fraction of a second before impact, you watched it fall. And your brain does something automatic. It assumes the object was pulled downward, by something invisible from somewhere below. That's the intuitive model. That's Newton's, and it was revolutionary for its time. Brilliant even. But it was also incomplete in a way that took over 200 years to fully reveal. Newton himself knew something was off. He called gravity action at a distance, meaning two objects could affect each other across empty space with no contact, no mechanism, nothing in between. And in his own words, not a direct quote, but the spirit of it, he refused to frame a hypothesis about how this happened. He just said, it works, and for most purposes it does work. Magnificently. But working and being true are not the same thing. Here's the first twist. In 1915, Einstein didn't discover a new force. He eliminated one. His general theory of relativity replaced the idea of gravitational force with something geometrically stranger, the curvature of spacetime. Mass doesn't pull. Mass bends the fabric of space and time around it, and what we experience as gravity is simply objects following the most natural path through that curved geometry. Pause and think about what that means. The apple didn't fall because something yanked it toward Earth. The apple fell because it followed the straightest possible path through bent space, and that path happened to lead downward. This is a simplified explanation to make the core idea intuitive. The full mathematics involves four-dimensional geometry that most working physicists need years to internalize, but the conceptual shift is real, and it matters. Gravity, in Einstein's framework, is not a force, it is geometry. It is the shape of reality at a given point. And here's where the first misconception gets quietly corrected. Most people believe that if you're standing on the surface of the Earth, you're being pulled downward by gravity. But Einstein would say something stranger. You're being pushed upward by the ground, in freefall. Like an astronaut in orbit or someone mid-jump, you're actually in the closest thing to zero gravity that nature allows. You're weightless. Your body follows the curve of space-time without interruption. The sensation of weight only appears when something, a floor, a chair, the Earth's surface, gets in the way of that fall and pushes back on you. Notice how your intuition resists. It feels backward. But every physicist who has studied general relativity encounters this same reversal. And it doesn't stop being unsettling just because you understand the mathematics. Now here's a deeper question that this immediately raises, and one will pay off in a moment. If gravity is just geometry, if it's just curved space-time, then what is space-time made of? What is being curved? This is one of the genuinely open questions in physics, and it sits at the intersection of general relativity and quantum mechanics, two frameworks that describe reality with astonishing accuracy but don't agree with each other at the extremes. Hold that question. We'll come back to it. Before that, there's a misconception that needs addressing. The rubber sheet analogy. You've seen it. A heavy ball on a stretched fabric, curving it, and a smaller ball rolling toward it. It's in every physics documentary ever made, and it is genuinely misleading. The problem is that the rubber sheet only shows curvature in space. It uses gravity pulling the balls downward to demonstrate gravity. It's circular, and it misses the time component entirely. The reason Earth orbits the Sun isn't mainly because space is curved near the Sun. It's because time runs slightly slower near massive objects, and objects move along paths that maximize their travel through time. This is called geodesic motion, and the curvature of time near a massive body is far more significant for everyday gravitational effects than the curvature of space. That's not a minor correction. That's a complete reframing of how the mechanism works. Here's a real-world anchor that makes this concrete GPS satellite. The GPS system in your phone, the one that guides you street by street, depends on incredibly precise atomic clocks aboard satellites orbiting about 20,000 kilometers above Earth. Those clocks tick at slightly different rates than clocks on the ground. There are two effects at work. The satellites are farther from Earth's mass, so time runs slightly faster for them, but they're also moving fast, so special relativity slows their clocks down. The net result is that satellite clocks gain roughly 38 microseconds per day compared to ground clock. 38 microseconds sounds negligible. It is not. If this weren't corrected for, GPS coordinates would drift by about 10 kilometers per day. The system would become useless in hours. What's remarkable about this isn't just that the effect is real. It's that this is time itself running at different rates depending on your position in a gravitational field. Gravity isn't a thing that pulls you. It's a gradient in time, and you experience it as weight. Pause and predict what happens next. If an object in freefall is weightless, and if the astronauts on the International Space Station are in constant freefall around the Earth, why don't they fall to the surface? Take a moment with that before the answer. The answer is lateral speed. They're moving sideways fast enough, roughly 28,000 kilometers per hour, that as they fall toward Earth, Earth's surface curves away beneath them at the same rate. They are always falling. They never land. Orbit isn't the absence of gravity. It's falling so fast that you miss the planet continuously. This is the second misconception addressed. Orbit is not a place where gravity stops working. It's a state of perpetual controlled freefall through curved spacetime. Now, back to the open question about what spacetime is made of. Here is where physics hits one of its actual limits. General relativity treats space-time as a smooth, continuous fabric. Quantum mechanics describes reality as fundamentally grainy, discrete, made of quanta. These two descriptions work beautifully in their own domains. General relativity governs the cosmos, black holes, galaxy clusters, the expansion of the universe. Quantum mechanics governs the subatomic, particles, fields, the behavior of atoms. But at extreme conditions, inside a black hole at the moment of the Big Bang, both descriptions are needed simultaneously, and when you try to apply them together, the mathematics breaks down. Infinities appear where there should be answers. This isn't a calculation error, it's a signal that one or both frameworks is incomplete. Physicists have spent decades searching for a quantum theory of gravity. String theory is one attempt. Loop quantum gravity is another. None has been experimentally confirmed. And this is not embarrassing, it's honest. Physics, at its best, is a discipline that knows exactly where its own maps stop being accurate. There's a third misconception worth addressing here, because it's one of the most common, that black holes suck things in like cosmic vacuum cleaners. They don't. A black hole has the same gravitational influence as any other object of the same mass. If the Sun was somehow replaced by a black hole of equal mass, Earth's orbit would not change. We wouldn't spiral in. We'd just go dark and cold. The black hole would exert no more gravitational pull than the Sun does now. What makes black holes extreme is proximity. Get close enough, past the event horizon, and the curvature of space-time becomes so severe that the path through time literally bends inward. There is no direction you can travel, not even at the speed of light that leads outward. The event horizon isn't a wall. It's a point of no geometric return. Here's a second real-world anchor, and it's one of the strangest demonstrations that relativistic physics is real. Muons. Muons are subatomic particles created when cosmic rays collide with atoms in Earth's upper atmosphere, about 15 kilometers above the surface. They are unstable. They decay quickly. Based on how fast they decay in lab settings, a muon traveling at typical speed should vanish within a few hundred meters. It should never reach the ground. Except muons do reach the ground, in large numbers, constantly. The reason is time dilation, one of the predictions of special relativity. From the muons reference frame, the journey is short because space contracts. from our reference frame. The Muons' internal clock runs slow, stretching its lifetime just enough to make the trip. Both descriptions are correct simultaneously. This is not theoretical. Muons arriving at Earth's surface have been measured, counted, and used to confirm relativistic predictions to extraordinary precision. Time dilation is not a thought experiment. It's something that happens to every particle you're made of, at every moment, in a way that depends on exactly how fast you're moving and exactly where in a gravitational field you sit, pause, and predict. If time runs slower near massive objects, does time run differently inside your own body? Your head versus your feet? Yes, measurably. Your feet are closer to Earth's center of mass than your head. Time runs, by a tiny fraction, more slowly at your feet than at your head. The difference is immeasurably small at human scales. It would take billions of years to accumulate a single second of difference. But the gradient is real. Atomic clocks sensitive enough have confirmed this at height differences of just a few centimeters. You are not a single object moving through a single flow of time. Every layer of you exists in a slightly different temporal environment, shaped by the curvature of spacetime generated by the planet you're standing on. The fourth and fifth misconceptions, often held together, are that gravity is the strongest force in nature and that it must eventually dominate everything. Gravity is, in fact, the weakest of the four fundamental forces, and it isn't close. The electromagnetic force is roughly 10 to the power of 36 times stronger at the scale of subatomic particles. This is one of the great puzzles of modern physics. Why is gravity so comparatively feeble? Why doesn't it dominate atomic interactions the way electromagnetism does? Nobody knows. This is sometimes called the hierarchy problem. Some physicists speculate that gravity may be leaking into other spatial dimensions we can't detect, which dilutes its apparent strength in our three-dimensional world. Others suspect gravity's weakness is a clue that our current description is wrong at a fundamental level. And as for gravity dominating everything eventually, it depends on what you mean by eventually. At cosmological scales and time scales, gravity does structure the universe, galaxies, clusters, filaments. But the expansion of the universe, driven by what physicists call dark energy, appears to be winning against gravitational collapse on the largest scales. The universe is not collapsing, it's accelerating outward, and we don't fully understand why. So here is where all of this lands. There is a pattern running through every twist in this story. Gravity confused with force, time assumed to be universal, orbit mistaken for weightlessness, black holes imagined as vacuum cleaners, gravity thought to be dominant. In each case, the confusion comes from the same source, treating a simplified model as a complete truth. Every framework in physics, Newtonian mechanics, general relativity, quantum field theory, is accurate within a specific range of conditions. Outside those conditions, the models break. And physics does something unusual among human discipline. It takes those breakdowns seriously. It doesn't protect the model. It follows the limit. This is the idea at the center of everything discussed here. Reality is built from limits. The speed of light is a limit. The event horizon is a limit. The Planck scale, the smallest length at which space and time as we know them make sense, is a limit. And when you push any physical law hard enough, you find that what looked like a deep truth was actually a boundary condition, a special case of something stranger and more precise. Gravity may be a misunderstanding, not because Newton was foolish, not because intuition is worthless, but because reality, at its foundation, refuses to be simpler than it actually is. The more carefully you look, the more the universe reveals that what felt like a force was always geometry, what felt like weight was always resistance, and what felt like falling was always the most natural path through a space that was never quite flat. The limits of our understanding aren't the edges of reality, they are the doorways into it.